Let's spend one more video discussing happy op-amp theory. This will be a little more abstract, and it's what I'm calling closing the loop. So we have our op-amp. It has two inputs, V plus the non-inverting input and V minus the inverting input, and it has an output that obeys the law big G is V plus minus V minus. And with negative feedback, so this is very important. That means that somehow there's a circuit attached to the output that comes back with a voltage that touches usually the negative side of the input of the op-amp. That makes the op-amp do whatever it needs to do to make the voltage difference between V plus and V minus 0. So that means that V plus will equal V minus, and then V out will be whatever it needs to be to make that happen. And then we can basically ignore the fact that G is infinity. That will come out of the equation, and we'll have simple circuits like our non-inverting amplifier, where now we have one V in and one V out. R2 and R1 is R2 plus R1 over R1 times V in. And this ratio here we call the gain, usually little g gain as opposed to big G gain. So the gain is the ratio of V out to V in. But we don't necessarily have to always build a circuit with resistors. We can do clever things, taking advantage of the fact that if we have negative feedback, the op-amp will do whatever it needs to do at V out to make V plus equal to V minus. So in this case, we'll build interesting circuits that don't necessarily have gains, but instead are control systems. And you're probably already familiar with a control system. Somewhere in your house you have a room, and there's also a heater. Maybe it's forced hot air, maybe it's a boiler. And in your room you have your thermostat that records the temperature. And if the room is, say, 65 degrees, it tells the heater to turn on. That makes heat go into the room heats up, the thermostat goes up to, say, 75 degrees because the room gets too hot. That tells the heater to turn off, and then the room can cool down. So that's a simple control system. And if you had a temperature sensor that went into an op-amp, the op-amp could compare that to a threshold of a desired voltage, could turn the heater on. As the heat increases, the temperature sensor would rise, and eventually that voltage would pass your threshold voltage. That would turn off the heater. And then if you had a plot of, say, temperature versus time, your heat would rise until it passed the threshold, and then it would turn off, and the room would naturally cool. And then the op-amp would turn it on, and then it would rise, and then it would naturally turn off. And that's kind of how the temperature in your room works. So let's see, how can we build this kind of control system with an op-amp? So we'll call this an op-amp. And the typical terminology is that this is a regulator. But we don't really have to pay attention to that. We just know that we'll have an op-amp circuit that is going to try to control something, and it won't necessarily be a simple circuit like we saw before with resistors. In this experiment, we're going to use the phototransistor circuit as our sensor. So when light hits the phototransistor, it lets some current go through this resistor. That current times its resistance creates an output voltage. And initially what we're going to do is we're going to have an LED source current from the output voltage of a sine wave generator. And we're going to point that LED at the phototransistor. So if we have a sine wave coming into the LED, we kind of expect the output voltage from the phototransistor circuit to be a sine wave. But you can already guess that that probably won't work, right? Because the LED has certain properties that say only when the voltage is above some threshold will light come out. And if we apply a sine wave to this LED that is sometimes negative, well, obviously negative voltage won't make any light come out. And even when the voltage is positive, we won't get any light out. So just by pointing a sine wave into an LED, we won't get a sine wave out from the phototransistor. So our goal is to get the same exact, maybe not the exact same voltage, but the exact same frequency and shape of output voltage that we have at the input here. But instead of having A1 attached to the LED, we're going to use the op amp. Now, that ends up being a relatively simple circuit, so I'm not going to draw it for you. You'll have to find that as you go through the lab. But let's build this first part of the circuit. So we will have the sine wave go into the LED. Light will come out. It'll hit the phototransistor, and let's look at what that output voltage is, and then think about how we can use our op amp to make the output voltage become a sine wave. Let's look at the components first. So in your baggie, we've got lots of LEDs. Notice that these little LEDs, this is a 3mm LED and it's green. It's kind of green because the plastic housing is green. So these are called indicator LEDs. They're nice for knowing if something's on or off, but they're not good at providing light. You wouldn't make like a flashlight out of these. This big clear LED though, it has a 5mm case. This is what they call a super bright LED. It's not red because it has a red housing. It's red because the chemistry inside makes it red. And this lens is a 5-degree lens. Or maybe it's 10 degrees. But the light comes out like a little spotlight, like this. The indicator LED is designed with a lens so that the light comes out like in all directions. So if you turn on this super bright red LED and look from the side like we're doing right now, it'll look just a little red dot. But if you look end on like this, it'll be a spotlight. It'll be a little laser. So yeah, don't look at that when it's on. So that'll be our LED output. Notice that you also in your kit have another 5mm LED. It's more opaque. You can't really see through the lens. This is another type of indicator LED that's both red and green. So we're not going to use that. We're going to use the super transparent 5mm LED. And then remember that the phototransistor looks essentially like the little brother of the LED. It's 3mm. It's got the completely clear lens. It also has a 5-degree input lens. So light hitting from the side, like what we're seeing right now, doesn't really affect it. But light hitting from the tip, it's very sensitive to. So it's kind of like the matching point of the LED. And what we're going to do is we're going to build a circuit so that they're about an inch apart. So the light comes out of the LED and goes into the phototransistor. And if they're not aligned very well, so if they're pointed like that, not much light is going to come out of the LED and hit the phototransistor because of those lenses. So we'll have the ability to kind of adjust how well this works by aligning them, as well as if you just put something in between them, right? That would block the path of light. If it was like tissue paper, then some light could still get through, but we can also block it 100%. So that's the circuit we're going to build right now. And now, how do you actually make the LED and the phototransistor point at each other? You literally will have to bend them. So here's the LED. I don't want to just plug it into A1 and somewhere in my breadboard. I need to bend it. So I'm going to grab it around halfway and bend it to 90 degrees. And remember, the long side is positive. So I'm going to put the long side in A1 and the other side in some row. And I'm going to point that in some direction. And then my phototransistor, I need that to point at the LED. So I'm going to take that and I'm going to bend it at around the same height. And remember, the long side is the negative side for the phototransistor. So I'm just going to build that somewhere on my breadboard. And I will need to apply 5 volts to my phototransistor and give it a resistor to ground, and I need a resistor to ground for my super bright LED. So let me find some resistors. I'm going to put a 10K, and this is a little experimental, but I'll put a 10K in series with my phototransistor to ground, because I don't really know, this is going to be a lot of light from the LED to hit it, so the voltage might be pretty big. If I wasn't, if I was just using ambient light, I'd probably need a much bigger resistor, like 100,000 or a million. But this will be a really conductive path right here. And then I'm going to use 330 in series with my LED, and that's to limit how bright the LED can get, so we don't burn it out. I might have given all my 330s away. Okay, I'll use 100 ohms in series. That'll just make it a little bit brighter. And I need a power wire for the 5 volts to the phototransistor. So I'll get out my wire strippers and just make a little red wire. I've got my op amp already in this board because we're going to need it in a little bit. But right now it's not doing anything. Now I need to see what's going on. So I'm going to hook up A1 to channel 1 so I can see what the sine wave being applied to the LED looks like. And I need a long wire so I can see what my phototransistor is doing. I'm going to make a long green wire. This will act as my probe so I can kind of poke around and see what's happening. Okay, so on channel 2, I've got my phototransistor voltage. So A1 is the sine wave. That's going to channel 1. V out is going to channel 2. I ended up actually using 100 ohms here. Either one is fine. And I used 10K here. But depending on how bright your room is and how far away you put the LED from the phototransistor, you can adjust these. So let's go into the Nscope app and see what happens. Okay, right now I'm just looking at what's coming out of the A1, and it's off, so I don't see anything. I'll turn on channel 2 so we can see the voltage coming from the phototransistor circuit. And if I block it, so now I'm covering it with my hand, and it goes down a little, and the light just in my room makes it that green line. So this is just not very bright, so the phototransistor voltage is not maxing out. Now I'm going to turn on the sine wave. And so it's going from 0 volts up to 1 volt. The LED needs something like almost 2 volts to even turn on. So the LED is not flashing or anything. We just don't have enough voltage yet. So I'm going to increase the voltage coming from A1 being applied to the LED. We'll go to 3.75. This is neat. I'm going to zoom in time. Typically, we only want to see 1 or 2 sine wave cycles per screen when we're looking at an oscilloscope trace. So adjust your time rate depending on the frequency of whatever it is you're looking at. All right, we'll flip back to the circuit just for a second so you can see what's going on. Here's my LED going on and off with that sine wave. It's pointed at the phototransistor. And what do we know about these voltages? So the red line, that's the sine wave coming from A1 going to the LED, pretty straightforward. The green line, this is the voltage from the phototransistor circuit. We can see there's a slight bit of like sine wave on top of it. I'm going to cover it with my hand. Okay, so now the only light that can hit the phototransistor is coming from the LED. That little sine wave went away. So the lights in my room are actually flickering a little bit. That's probably because I have these like cheap LEDs to illuminate my camera rig here, and they're flickering at maybe 60 or 100 hertz. So that's actually that little bit of fuzz on top of the green line, so that I can make that go away if I block it with my hand. When the red line is below something like 1.8 volts. The green line is probably flat, and that's because when the LED doesn't have at least 1.8 volts, no current will go through it, so no light. So no extra light hits the phototransistor. As soon as the red goes above 1.8 volts, light will come out, and that's what hits the phototransistor and makes that go up. Okay, so that's pretty cool. If that signal, the green line, is what we wanted, then we would be done. But here's the problem. And I'll switch back to show you my circuit. What if somebody came and knocked my LED out of alignment, so it's no longer pointed well at the phototransistor? Or what if they stuck their finger in there? Or what if it was foggy and the light just couldn't hit the phototransistor anymore? Let's see what that voltage looks like. So I'll move the LED over, and now it's not really pointed very well at the phototransistor, so the green line is a lot smaller in amplitude. It's just not getting as much light. What if I push them closer together? Now so much light hits the phototransistor that the green line gets too big. And if I kind of put my finger in the way, I could even control how much voltage comes out of the phototransistor by kind of wiggling my finger. So this does not have a control system in it yet. I'm just blindly applying a sine wave voltage to this LED and seeing what I get out of my phototransistor. So my goal is going to be to get a sine wave back out of my phototransistor, and regardless of if I stick my finger in the way or misalign the LED, I will always get that same sine wave back out, because instead of the sine wave going to my LED, I'll have the sine wave go to the op amp. The op amp controls the LED, and then the LED, of course, points at the phototransistor, which provides another input to the op amp. So as a block diagram, we're going to have our, we'll call it desired voltage, which is our sine wave. That's one input to our op amp. We'll have the actual voltage, this is the phototransistor voltage. That will also go to the op amp. The op amp will control the LED, and the LED, of course, is pointed at the phototransistor. So what will the op amp do? It's going to try to make these two voltages equal by doing control on the LED. And so the LED is going to, we don't know what it's going to do, some kind of sine wavy type thing to control the voltage coming out of the phototransistor so that it tries to match that. So follow along with the lab sheet and see if you can build this circuit. You'll build it two different ways.